Hello, everybody. It's great to have a group of little white names in black boxes. And it'll be even greater when we can see you in person again. So hopefully hey, here's some faces. Yeah, thanks. Just continue to get used to this. All right. Well, Scott Farbman and I are excited to share this with you, and we want to leave time for conversation at the end, questions, et cetera. So first thing I want to say is that you can get CPHC continuing ed credits for this, and that verification code is the one to use, 22120. And that takes me back to underscoring what Tony said. The website has just been updated, the Phius website, at last. And it's still getting its massages, but boy, is it a different animal from what it was before. So I hope everybody's gotten onto the portal if you're a professional, a rater, builder, CPHC. So check it out if you haven't. All right. We are going to talk about a multifamily project that Scott and I have been working on for a little over 2 years. And those of you who were here in February of 2019 saw a presentation at the beginning of this project. And so this is some recap of that and a lot of things that we've learned. The team just issued for permit. I am not the architect of record. I'm the CPHC on this project, where Malcolm is the architect, but Scott's firm, DBHMS Database, is the MEP engineer, and we're really glad about that. They've been so instrumental in really making this happen. So let me jump right in. First, a little intro from each of us. I'm Tom Bassett-Dilley, architect and CPHC, and one of the founding members of this group, which, gosh, it's been over 10 years. Just kind of amazing. And the project in the upper right was the one I was working on when we founded it. It's a non-certified passive house, I'll call it. And we've done a bunch of passive house projects in zero energy capable or zero energy, including some retrofits. And there's a few on here that are recently certified or pre-certified passive houses that I got to add to this slide. So it's a growing number. We're fortunate that all the work we're doing in the firm is either a deep energy retrofit or a new passive or zero energy project. So that's exciting for us, and we're always happy to come here and share it. And focusing more and more on retrofits, because that's what we got to do to decarbonize. To you, Scott.
All right, Scott Farbman. Know most of you, so I'm representing the MEP engineering side of things today. So many of you have probably heard of DBHMS. We're traditionally an MEP design firm. Our group Database Plus is kind of our rebranded high performance studio that does all the energy modeling, carbon modeling now. So I have to compete against Tony at HOK, and all of our green certification work as well. So I've been lucky enough to get tossed into all this passive house work, and it's become a real passion of mine. And I get to kind of tiptoe between architecture, CPHC, and an MEP engineer. And I think it is inherently super interesting. And then at the same time, I really get to help streamline things when it comes to these projects. And I think that's important to keeping costs down and getting certified projects at the end of the day. So, Tom, back to you.
This is a rendering of the project as seen from Columbus Park, which is basically the park that's on the east side of Oak Park. So it's where Austin runs up against Oak Park. And Columbus Park is a big, beautiful park designed by Jens Jensen. The site is owned by the Oak Park Residents Corporation, which is a big property owner in the village, and they've worked with the village in public-private partnerships, et cetera. But this is a privately owned parcel that currently has a small kind of California-style, I believe, 6-unit building on it that needs really intensive work. They decided the best use of the parcel would be to actually rebuild. So it's this interesting kind of gateway moment where as you walk on the north side of the building, they've created a colonnade, which allows the building to kind of go out over the sidewalk. And that colonnade leads you towards a new crosswalk over to Columbus Park. And of course, up from the roof deck, there will be views of the skyline. So it's a really great location, but this side of Oak Park has been devoid of any investment for 50 years. Really, I mean, it hasn't, I should say, there hasn't been any large developments. So this, you know, large, it's 44 units of residential over a story of parking. It's 2 blocks north of the Blue Line in Eisenhower. So it's got some good walkable aspects to it. It's 80% market rate, 20% affordable units, which is right in keeping with Oak Park Residence Corporation's mission. And we started out the project with David Pope, the executive director, who's been really the energy behind the project, saying, you know, what can we do for really making this a building that would really set a great example. So we started talking about the Illinois Clean Energy Community Foundation grant, and he said, well, great, let's go for net zero. I was like, oh, okay, let's do it, I'll help. So it was quite a process getting the ICCF, you know, through the process with them, mostly because it's a mostly market rate project, and we'll talk about that when we discuss metering and whatnot later on in Scott's portion. But eventually we came to an understanding that worked for everybody, and we're able to do this thing which kind of pushes the limits of density. 5 stories of residential on a fairly small site, a lot of people, a lot of energy being used, and not a lot of roof area to put solar on. So, but we're right there. We're right there making it barely on the edge. And it's a little scary, but I say scary only because the last 40% of that grant is contingent upon achieving net zero that you've proven out through a year of bills, of, you know, of data. So anyway, it just got through the entitlement process. The public reaction was basically, you know, we want more parking, and yet the sustainability efforts outweighed that. So it won the day with both the Plan Commission by a split vote, 4-3, and the village board was unanimous actually. So quick view at what the building and how it's laid out. This is the ground floor plan where we have parking spaces with the exit stairs coming down. The one on the left-hand side, which is the east facing the park, enters into that lobby. The lobby really is at the corner there, so it looks out to the park. And then the elevator is there. We have sort of electrical and plumbing rooms on that first floor. Second floor, as you go up that main stair, comes out in sort of the amenity area of the floor plate on the second floor only. And then the rest of it is units. These are mostly 1-bedroom units, the A units you're looking at there. And then there's a couple of studios. I guess this floor only has 1 studio. And then the typical floors are more like this, where you've got a 2-bedroom unit up there above the amenity space, and then 1-bedroom units. But you know, there's some interesting things. It's a double-loaded corridor, but David, the executive director, is really wants this to be high-quality experience. So you know, making sure that those corridors end in windows, not in a dead wall. He really wants this to be a beautiful building, not just an efficient building. You know, so it's been great to have an owner so committed to quality on all levels. So how do we make it a passive house? We got some backstory on that, which we'll get to in a second, but just in general, you know, we've got wood frame over the type 1 parking. So it's a precast base. We've gone back and forth between cast in place and precast. I'm pretty sure we're still at precast, but basically concrete over the parking. And then we're going over on top of that with, you know, EPS insulation. And it's basically a fireproof wood framing for the 5 floors above. So we are at R37 on the walls, 2x6s with exterior EPS. We have a R75 roof right now with a whole bunch of tapered polyiso. But we don't need that from a space conditioning standpoint, but from site energy, we do. We'll talk about that in a second. The slab is R26. So you see these are not crazy, crazy wildly high R values. The roof is a little high, definitely way above code. And then the windows U value is 0.18. And the solar heat gain coefficient everywhere, all sides, is 0.2. We have low gain glass. And you'll see why when we look at the energy modeling in a minute. Windows have been a real eye opener on this. When I think about the difference between this building that we're modeling and all the single family work we've done, it's a different animal. So in terms of modeling, actually when we did the presentation back in 2019, we kind of traced the path from Phius metrics inheriting the PHI, 4.75 standard, to the Phius 2015 and then 2018, which is what we were using then. And then in the kind of code cycle level review that Phius does of the standard, they give us updates on this calculator here on the website. And so you see we started at Phius 2018, and when we put in our envelope area relative to the ICFA, the interior conditioned floor area, and we put in the ICFA per person, we got these, it spits out these results. So what's really fascinating about what's happened with Phius as a standard is that it is not only climate specific, but it's also building density specific. So it really is taking into account what's going to happen in a building with 90 people in this kind of square footage versus a building with 30 people. They're different animals, and you got to think about the envelopes differently. So the standard is definitely getting more nuanced in this way, and it's kind of built in behind the scenes in these calculators. So Phius 2021 calculator version 2 there is what we were shifting to, and you can see a relatively big jump in like the annual heating demand. From 2018 when we were at 4.6, and then it went up to 5.7 and the kind of interim Phius 2021, and now we're looking at the version 3 and at 6.2. So if we had designed it underneath 4.6 for the heating demand, and now we have a lot of headroom available to us. So what's happening with the standard, as you can see, is that the envelope metrics are relaxing a little bit, but the primary energy metrics, the source energy metrics, is not relaxing. In fact, it's getting more stringent. So it's leading us towards net zero, but not making us do it strictly with the envelope. We got to start getting into renewables. So that's a little wonky, but that's why we're here, right? So WFI passive modeling, we do the SketchUp model of the thermal envelope, and we assign the WFI passive properties to opaque and transparent areas. For ourselves, just to keep things clear, we color code it. We make slabs blue, we make walls, opaque walls pink. Import that into the energy modeling program, WFI passive, and start messing with it until we get it to work. So here, when you look at these results, you can see heating demand on single family houses is usually the hard one, or heating load, or both. But you can see we got miles of room there, relatively speaking, from the heating demand relative to the peak, or the limit, excuse me, the maximum we're allowed. And it's because this is a dense building. There's a lot of people in here. And so we're actually creating a lot of internal loads, and cooling is our bigger issue, even in this climate. That's why we went with those low solar heat gain glass as a solution, as opposed to what we do on most of our single families is like high solar gain glass on the south, low or moderate gain on the east and west. And so we're getting the happy green check marks like we want. Source energy has the angry red X, and that's because we're using that to tell us how much energy we need to provide with solar. So if you look below source energy at site energy, you can see that number there for total, maybe not if you're on a phone. It's about 199,341 kilowatt hours per year that we have to make to offset the energy to get to net zero. Now, in talking to Lisa White about this at Phius, she says they've been monitoring a lot of buildings, and they've seen a pretty consistent, about 8% factor that buildings tend to run just a little higher than the site energy. So we're multiplying this total by another 8%, but you can see in a slide coming up that this is a real big question. Are we gonna be net zero, and how are we gonna control that? Okay, so a couple more kind of things that come out of the model. The model's really cool. Some of these output graphs that are built in to the Woofy passive software are interesting. And once you've looked at them a while, you can start to see things that tell you a little bit about how this building is going to feel and perform. This on the left, the winter energy balance versus summer, is kind of just showing us where the energy is coming from and going to. So basically, the blues are losses and the reds are gains. And in the winter, you can see we're losing a lot of heat to the windows, and we're losing a fair amount through ventilation. Ventilation, everybody knows, takes energy to run, and you're also you're bringing in cool air and you're transferring heat to the outgoing, but it's an energy consumption. And then the walls is the next one. Then everything else, slab, roof, etc., is relatively minor. But then you look on the other side in the winter, and internal gains is a lot. There's a lot of people in here. We don't need a lot of big windows heating us up. So that little slice at the top of heating, that's mechanical heating. We just don't need a ton of it because we have such a dense building. Then over in the summer, you look at the same thing. It's like, oh my God, internal gains are killing us. We have all these people and all their TVs and all their lights, and they're showering and they're cooking, and we have to cool it down. And if you look at the graph on the right, that shows us how much energy we're using to heat in the red in the heating season, and then cool June, July, August. I mean, July and August is being, that's the peak energy of this building. It's going to be cool. And I shouldn't say that's not the peak load. That's like the consumption, the total demand. The AC will run more than the heat. And then you've got these October, November, April, May, where almost no energy will be used, but we'll be gaining solar. So those will be our great, make energy months. So here's the thing. We're designing a multifamily building that's going to have like 90 people in it. And when you look at the electricity, because this is an all electric building, then, where is that electricity being used? Well, the heat pump heating is like, the second biggest chunk, and that's heat pumps for both heating and water. Cooling energy, relatively small, because these are really efficient systems that Scott will talk about. There's auxiliary energy, but then there's this appliances. Appliances is actually everything that residents control, and some things they don't, like hallway lighting, but mostly it's like lighting, refrigerators, cooking, TVs, plug loads, and look at that, it's gigantic. And if that gets just a little bit bigger, then we're sunk net zero wise. So there's going to be a campaign here to talk to residents, and we're going to be required by ACCF to give them energy monitoring and try to create some kind of incentive whereby people don't just leave a bunch of TVs on all the time, because that would be a problem. So you can see our total demand just under 200,000 kilowatt hours per year. So yeah, occupant behavior is a big thing. No net zero buildings, just net zero the way they're used. Let's put it that way. So just to kind of recap where we were in 2019, we started this building with the owner's wish to have a lot more glass than we wound up with. And there's nothing we could do with our values to make the building work from a cooling or in some cases heating load standpoint. That was when we started like 37% glazing percentage of wall area. When we got it down below 30, we got to like 27%. Everything got easy from a insulation standpoint, but we had to be careful about shading. We had to look at, these balconies. Frankly, they're a good amenity. They're also doing a lot to to keep us from overheating and stuff. So a little bit more about windows. If anybody doesn't follow Building Science Fight Club on Instagram, people who do Instagram, I totally recommend it. Christine Williamson is brilliant. And she grew up with this in her blood because she's the daughter of Joe Stiebrick. And she teaches building science to architects. But she puts these super insightful posts out. And this post, Why Glazing Matters So Much More Than Insulation, was interesting because she's doing the math on a wall. You know, it's like, so you got this R30 wall and you have these terrible windows in it. What's the effective R value of the envelope? You know, it's an eye opener. And so what I have here is Woofy passive output from two different projects. The project, our multifamily here up on top, and then on the bottom, it's a house that we recently got certified down in Southern Indiana. And the one on the bottom shows what we normally are looking at. Like the south windows are gaining more than they're losing, you know, in the heating period. And we know that east and west and north aren't going to gain in a good way. So we keep the size of them modest, and we have most of the windows in the south. That's like ideal setup for passive building. But look at the top one. I mean, this is what, like, this multifamily building is loss, 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 loss. And we have to do that because if we didn't, we just overheat like crazy. So it's been such an eye opener to me. First of all, the difference between a passive single family versus multifamily, and also the fact that doing a building with a lot of glass is a nightmare energy wise. Even the best glass out there, which is phenomenally expensive, is going to be a lot of energy to heat and cool, and it's going to take bigger heating and cooling devices because your peaks are, you're going to have to provide more heat when it's really cold out. You're going to have to provide more air conditioning when it's really hot out. Unless you have like tons of elaborate shading. It's like, it's a hard way to do it. It's just, this is something that architects have got to get out of their heads, and owners have to get out of their heads, that like tons and tons of glass is the way to go. And also, you know, from the biophilic design standpoint, there's some arguments we could go down rabbit holes about that. Is it really connecting you to nature when you have tons and tons of glass, or is it making you feel something else, exposed, or et cetera? So again, back in 2019, when we were starting with PV watts and looking at our, you know, what we could do with the solar array, owners wanted a lot more open space to get good natural light coming down into that roof deck amenity space. Couldn't do it. And pretty soon we were like, hey, you know what? The roof isn't actually even quite big enough to get all the solar that we need to get up here. What are we going to do? So we said, you know what? Let's get a solar vendor on board. And Scott, jump in anytime you want. But basically, you know, we're not solar. We don't have the tools that solar experts do, like some of their LiDAR and the really more accurate climate modeling and knowing exactly what the inverter efficiency is going to be and how much you might need to worry about with like degradation or soiling if you're at 10 degrees at the panel versus 40. You know, there's a lot to know to really model accurately. So we were like, you know what, let's just get us in the ballpark with PV watts and get a vendor on board. Well, getting a vendor on board was tricky because this project is not like just climb up on a roof and put some rails down and put some panels on it. On the south side, we have to create a steel racking system that they have to attach rails to. And on the roof, we have it raised up, and there's access issues about getting up to put those on. So there's more thinking to do. And if you're already stretched in capacity, you want to probably take the easy jobs. I mean, I'm not saying that any of the vendors said, oh, this is too tough, but it's kind of what it's felt like. That we got some bids, and then people backed out, and then other people gave bids, and they didn't seem to really understand what we were asking for, and it didn't add up to the output we needed. And so it's been a little bit crazy. So we've been just continuing to kind of essentially try to model this and bring it to the vendors in a way that they can understand it better. You know, I mean, like creating these 3D views. Okay, there's going to be this steel superstructure, and then the rails can go on that, and you know, we're assuming the panels are these 39.5 by 79 inch panels at 400 watts. This gives us the output we need, et cetera. So anyway, we're getting close, we think, but we are totally covering that south, well, I shouldn't say totally. We're creating a small window for sunlight to come in more, but we're angling the panels up at 10 degrees so you can kind of see through to the sky as you come up and out. So it doesn't feel like just a completely opaque roof. We talked about using bifacial panels that let some light come through, but we need the output. So bifacial panels are more expensive. In some cases, they give you more, some they don't. That's one of the questions we have for vendors who aren't on board yet. Could we get more output with bifacial, and we can make some of that difficult south side go away? So yeah, we're on tenterhooks here with the solar because obviously a whole bunch of our grant money is riding on this. Scott, you want anything more before we throw it over?
I think that the conversation about bifacial has been interesting because they don't have the simulation data and experience yet to not even, they just don't want to make a good estimate on what it could produce above and beyond a normal panel. So in order, it seems like a good idea in theory, but production is going to be totally up in the air. So like Tom was saying, we need to rely on more traditional panel technology, even though we're being tempted by this new technology that seems attractive, generating power on both sides. But the thing that is driving me nuts is the uncertainty and the fact that we need to hit net zero in operations in order to get, a large amount of grant money. So it's been a struggle. People are scared to get involved in this project because of the south wall, and also because there's a lot of stakes here at hand. And but yeah. Also I want to commend Tom for really going outside his shell and becoming a solar designer here. It's been a fun process working together and trying to figure out what is even reasonable to project on solar production here. Yeah. Let's be like super conservative and say like worst case scenario, we're at 190, 200. That's a little bit lower than we want. So here's solar provider. Here's all our assumptions. Like, what did we do differently? Inverter efficiency is something that Tom mentioned that we found to be a little bit different on their models. It's been a great learning experience, I guess.
Yeah, at least that. Yeah. And I gotta say, it's weird times. I mean, like some of this apparently is also what panels are available, and we're finding this also with like the polyiso tapered roof insulation. We're designing that for a house right now. We were just told by a contractor we can't get that for residential anymore. It's all being sucked up by commercial. It's just not available. And so this like just not available thing is happening. And it's weird, man. I mean, it just goes to show that, widespread warfare and pandemics, I mean, they matter. World peace is actually important for construction. So I'll just put in a plug for world peace. Scott, is it okay if I just advance, or do you want me to throw this over to you?
No, you can advance. I think okay. Another interesting thing with the solar panel stuff to consider is in a project like this, when we're planning what it needs to be, and we're at a point where we could purchase panels, we wouldn't be installing them until, a year or two later. So you really have to, it's a complicated calculation there. Do you risk pricing and wait for technology to advance? Like we could lock in a 400 watt panel today for this price, but if we're not installing them for 18, 24 months, like what does the panel look like at that point in time? Is it a 430 watt panel? Are we going to be able to produce more energy? Do you wait to buy the panel then, or do you buy them now and store them in a warehouse? It's been that sort of calculus isn't something I've considered in the past either. And I mean, it reminds me about, if you've ever built a computer, any hardware you buy that day is like instantly old technology the day after. And really seeing that trickle through at the scale is mind blowing. Okay, we're gonna jump into some system stuff. This First slide, early days, a lot of people want to say, let's do geothermal. It's got to be the best. When we really ran the numbers on our energy models, we found that on this building typology, especially on high performance buildings that have a lot of value in the thermal envelope, so heating and cooling loads are really minimized, that the extra coefficient of performance, or COP, that you get from a geo-exchange loop on your heating and cooling systems, while it does increase it, pretty high 5+ range, the amount of energy you're spending to heat and cool the building is pretty minimal. Tom showed it on Woofy a little while ago. Space heating and cooling is really, a small slice of the pie. So what we found is, yeah, a ground source exchange, a geo exchange did improve overall energy use. In this instance, it was about 3%. But if from our perspective, it wasn't enough to recommend that system because of the significant extra cost to do the drilling and the loops and all that. It just wasn't something that we advised. I think that said, there's a scenario in which it could make more sense as we start to look into more life cycle carbon emissions, opportunities to reduce refrigerant load in the building. There's other considerations to be made, but at this point in time, the air-cooled heat pumps perform really well, and we have stuff like Hyperheat from Mitsubishi, same types of technologies at a commercial level too. Really, the coefficient of performance, even at -10 temperatures, is still quite good. So energy to energy conversation, we're not seeing that big of a change here, and that's why we ultimately ended up with an air-cooled VRF. Schematically, this is what it looks like. We've got a condensing unit on the roof that serves a stack of units here. So one outdoor unit serving multiple indoor units in each cluster of apartments. And then we have a centralized ERV providing fresh air and exhausting from all the units as well. And with heat recovery there, that's in the 85% recovery rate. And that's another thing that we need to keep a close eye on, because if you have lower heat recovery and you're moving a lot of air, that could really sink your heating demand or heating load requirement. So that was a diagram, schematic. This is what it looks like in reality when we're designing the system and talking to manufacturers and really figuring out how all these indoor units work together. A little bit easier to understand on a single family home if maybe you have one or two mini splits or a couple indoor units attached to one outdoor unit. But in this instance, we have a corner apartment. In this example, we've got 3 indoor units per apartment, and then it stacks up every floor, and we have one outdoor unit up there on the top left serving these in a stack. There's a couple other ways to do this. So we've seen it be, let's go back for a second. So we went vertical stack here. We assessed very early, there's a heat recovery option to VRF. So there's a branch box and everything comes back, and you can recover, you can trade off efficiencies in your indoor loop. If you have some places calling for heat, some places calling for cooling at the same time, you could reap some of that in the loop efficiency and design. In order to do that, we would have had to do more of a horizontal split. So maybe we have one outdoor unit per floor, and maybe the south side is calling for cooling and the north side is calling for heating. East and west changes throughout the day. That's something that we could do, but again, we didn't really find energy savings at a heat recovery level. So ultimately, we found it easiest to design and implement a vertical stack, and that's going to cut down on refrigerant lines as well, and then cut down on total refrigerant charge and load in the building, which is something that we're starting to pay close attention to now that we know that refrigerant is a pretty significant carbon emissions impactor. So we can move forward. On the next screen here, so this is our ventilation approach. Diagrammatically on the left, one unit on top serving all the individual units. We've seen a couple other approaches be analyzed. There's a unit by unit approach. So you might have more of like a single family sized ERV in each dwelling unit that is serving it directly. On another multifamily project, we're looking at a floor by floor approach. So you have a slightly smaller than a centralized unit sized and ducted to each unit on that floor. Some challenges there is you have a lot of horizontal ductwork and your corridors become very tight, and it's hard to coordinate all of those duct runs with other things you have to coordinate, other plumbing, fire protection, etc. So lately, where we found the best kind of compromise is a centralized unit on the roof. And then on the top level ceiling, we do all of our horizontal ducting. And then we go straight down in vertical stacks and serve all the individual units. And this is what we've done for now. We do want to keep an eye on these individual unit by unit approaches. I think it's something that could be really effective and really simplify the way the building can operate once it's built. If Eco Achievers is on the call, they'll be the first to say that these centralized units are tough to balance, and it's hard to guarantee that all the airflow is going to the right places. But we're pretty confident from a design perspective that it works, and this is what we've been doing on the past couple multifamily passive house projects. Here's some energy breakdown graphics. On the right-hand side, that's based on our current modeling, our updated modeling. And on the left-hand side, that was our early phase modeling. I think we showed that graphic back 2 years ago. Interesting to note the way that metering is broken down. There's going to be a meter on the house side, which will provide, they're connected to the outdoor condensing units for the VRF. So heating and cooling is specifically on the house, as is ventilation because it's a centralized unit again. And then any common areas are on the house as well with lighting, plug loads in our amenity space, things like that. And then on the tenant side, it's the bulk of, plug loads, TVs, laptops, your appliances, things like that. And then we have individual unit by unit hot water heaters. We like the A.O. Smith product right now, the hybrid heat pump hot water heater that they provide. So, at the end of the day, it gets split up pretty close, 50 to 50. And if we look on the right-hand side, this pretty well reflects what Tom was showing on his WFI model, where internal equipment, our appliances, plug loads, et cetera, is about 50% of the energy use on the building. And that's, to me, really wild to think about. We typically think space heating, hot water, et cetera, is going to be the driver here. But when you really have a high performance building and you don't need that much space heating and cooling energy, it all goes to plug loads, things that we can't really control. And that's the scary part. That's why I've been saying in chat that I'm so scared about hitting net zero when half the building is all about occupant behavior. And again, that scares me because we can't control what they do. Here's this, a lot of numbers on the screen. You don't have to read them all, but we did a lot of energy model vetting between the programs that we use at DBHMS, not only to size equipment, but to do our own energy projections. And we cross-check them against the WFI model. Not that we don't trust what Tom's doing, but we do, WFI at the end of the day is about calculating heat loss through your envelope. It doesn't do system analysis quite as well. We say what a COP is, and then it throws that at the heat loss, and then that's how we have our heating energy. So we really want to spend some time making sure that we feel good about all of the inputs and outputs. And just on the screen here, I thought it was interesting to highlight one discrepancy that I saw, and we talked through with Tom and his firm, the protocol to analyzing cooking energy on the range. And right here on the right-hand side, I have summarized 3 approaches just to throw it out there. So the WFI Phius protocol is based on a kilowatt hour per use, and they estimate 500 uses per person, and we've got 87 occupants. We end up at about 9,000 kilowatt hours a year. ResNet does it a little bit differently. They've got some efficiency ratios here, and then that 331 plus 39 times NBR is 331 uses, and then there's a modifier based on number of beds. So it ends up being, almost double 14,200. So a little discrepancy there. And then you go into what we would do at DBHMS. We reference PNNL, which is the Pacific Northwest Laboratory. And they have a certain schedule that says there's 555 hours a year in which you're going to use this range. And this range, if it's induction or electric, whatever it is, has a peak use of 3 kilowatts. You turn that on full blast, it's pulling 3,000 watts. Say you turn it on medium low, it's only 1,000 watts. We'll apply that throughout the year, number of dwelling units, and we could see upwards of 73,000 on peak and as low as 25,000 on the low end. And again, just want to show that at the end of the day, the energy model is only as good as the assumptions we can make. And there's a lot of variance and discrepancy across the modeling platforms. And, who knows best? I don't know, but we're going to find out. Again, this is what scares me. The fact that cooking could be as much as 70,000 kWh a year. That's, like 40% of the total energy use of the building right now. That to me is mind blowing. So I'm scared, I'm excited, lots of emotions, but just wanted to show some of the, the back end calculations here and considerations that need to be made if we're chasing net zero, and it has to be done in operations. And then I think we might be ending on this slide. I think it's good to talk about some of the challenges we faced and discuss some of the interesting things that we've come across. And the number one thing here is this building wouldn't be built like this if it wasn't for the ICECF grant and the $2 million that comes from that awesome organization. And I do think one of the reasons that this building got approved is because of the efforts it's being made to take things to the next level in terms of sustainability. It's, people on the council said more developers need to do this. And they weren't even just talking about net zero, they were talking about electrification. They're talking about other things. So really, the industry needs to catch up to this sort of design, and hopefully this project is going to help pave the way for that in our region. As I noted, occupant behavior, there's a lot of variability there. So we're doing our best to capture that. Tom ran a series of sensitivity analyses and iterations that said, let's see what happens if we have another year of COVID and everyone's working from home and we jack up the plug loads and miscellaneous electrical loads times whatever. And then let's make sure we're including that in some of our annual projections on solar to make sure we don't get, bit in the butt later down the road. And that's a really interesting component of this whole project. It's not just about the building design, but it's about predicting the future in worst case scenario. Energy monitoring. This is another thing that's, I don't know if it's required, but it's being asked of us from ICECF. They really want to be able to see what the building's doing in real time, not just at a whole building level, but by, in an apartment by an apartment level. And if you can add controllability on top of that, even better. So imagine like a phone app that lets you control lights, thermostat, all that, smart technology. And what we're finding is this is an emerging market. We haven't found a product that kind of does all that for you. And that's been a bit challenging. Like do you have a submeter on every individual electrical distribution in each dwelling unit? What kind of math needs to be done? Is it an accounting exercise? Are we actually submetering? What do we do? And then finally, technological capabilities. This one's kind of obvious. I talked a little bit about it with the solar panels, but systems and performances are always evolving. Does that mean VRF is going to be, the lowest energy use option next year? I don't know. Maybe it is, maybe it isn't. Are other things going to become cheaper? Probably. So we'll have to see. And with that, I'm going to mute because it pains me for all you to hear the dog. All right. Thanks.
Scott, is your dog's name Meter? I'm just curious because when you're saying Meter, it started barking more. Come here, Meter. Yeah.
No, but we should change that.
So I did actually want to ask you a question, Scott, and about the VRF system, because it's an air source heat pump. Something people always ask about with mini splits or other like residential single family size systems. Do you have to worry about backup heat? Are we worried about polar vortex and these things don't work, or do they have a better turn down or low temperature function?
We're seeing that the newer iterations of the heat pump work really well down to -10. That's what they're specified to. Of course, capacity at -10 isn't that great. So you're challenged in the fact that do you oversize for worst case scenario, which is something that we're definitely not trying to do. And then also another thing that we've seen over time is wind chill is brutal. If you could protect those units from the wind in the colder months, you're going to get better performance out of those outdoor units. So we're trying to screen and protect things as much as possible. Yeah.
I wanted to jump back into the chat and answer a question that Janet put up. If the big picture is net zero, wouldn't an efficient building, modestly efficient, supplied by community solar meet the mark? Why should we care about figuring this all down to the detail? And I think it's a great question. It brings up a lot of issues about electrification. But Janet, to answer your question straight up, we're doing it because the grant requires it. The grant requires that we produce all of the energy that we consume on site. And that's just the way the Clean Energy Community Foundation Net Zero Building Grant works. But Phius will allow you to use some grid solar to achieve the Source Zero certification. So Source Zero is Phius's name for net zero. And you can use some. And I've never tried that, so I don't know the number off the top of my head. But go ahead, Scott, you're going to say.
Yeah, I was going to say, so you are allowed to do that, but Phius has derated off-site energy. Community solar is derated by 20%, so you get 80% of every kilowatt provided. And I think you could even do renewable energy certificates still, but they derate it down to 20%. You get 0.2 for every kilowatt hour provided. So they give you some flexibility there. But like Tom said, ultimately didn't jive with the grant. And I do agree that large scale community solar and things like that could be where we need to go with things. But
really fascinating conversation that happened with this group I'm with, the Oak Park Climate Action Network. We've basically instigated, and the village has hired a consultant now they've just created the greenhouse gas inventory. They've implemented grant programs, $10,000 up to $10,000 for rooftop solar, or for building efficiency. 50% up to $10,000. So big incentives for people to improve their homes, because the greenhouse gas inventory shows 73% of our energy consumption in Oak Park is from buildings, as you expect with old, leaky, poorly insulated buildings. Anyway, we were on a call with this group, and there's a guy who's a physicist, and he's talking about electrification. And if anybody hasn't read Electrified by Saul Griffith, I really recommend it. It's a fascinating book, which basically says, if you want to decarbonize and beat the climate crisis, the only way is electrify now. And he kind of throws conservation under the bus a little bit, which we were talking about on the Phius Council today, that we need to counteract that message a little bit. But the point is that the physicist on the call was saying, you can't just wait for the grid to clean up. You have to create more demand, and they're going to meet the demand with renewable energy because it's cheaper to do than coal now. So it was kind of a fascinating thing. Anyway, electrification is definitely the direction we need to go. And that leads to your second question, Janet, which is, in terms of generation, is there interest in Oak Park for neighborhood microgrids? And I think there is interest, but I got to say, I don't know enough of really what defines a microgrid relative to the utility and everything like that. Scott, can you talk to microgrids at all?
I can talk to it a little bit. I know it's like Bronzeville, I think, is one of the first pilot microgrid communities that ComEd had a large role in. But at a high level, it's, you know, a series of buildings or a neighborhood that are all interconnected to each other, and they're able to run off of, you know, separate from the larger grid at a whole.
Basically, they can island in an outage. And so IIT has been very involved in it. So that would be the group that I would go to locally to find out how it's working and their experience with it. But the other advantage with it, so the reason I'm asking is that these questions is a little, I've got something behind this. How would you scale up what you've been able to do here? Like if you were asked to do a development that had 10 buildings and you could use community solar or build a microgrid into it, what have you learned here that is replicable that could scale?
That's a great question. Well, I think as you can see from the nature of this building, that getting on-site net zero at this scale is a challenge. I mean, we're having to, you know, jump through hoops and, you know, create this heroic PV array. So if we're at 4 stories, it's easier. If we're at 3 stories, maybe we can just do it on the roof. So I guess scale is one of the things we've learned, that if you're really densifying, you should not be counting on local, you know, on-site generation unless we get into things like solar PV glass, et cetera. I think the idea of the microgrid is a good one, and that perhaps what we should be doing is targeting a level of consumption that is, we can really feasibly provide all of our electricity needs with renewable energy. And this is a question that I've been trying to really kind of dig into with a calculation standpoint, which is like, if we just electrified everything now, we need to have, Saul Griffith says, I think like 2 to 3 times more electricity production in the country. So, you know, double the transmission lines, double the power plants, or all of a sudden there's solar everywhere and there's a whole lot more wind farms and offshore wind and onshore wind. So I think that some conservation is absolutely critical, and then you meet the demand with efficient buildings, but I guess what I'm saying is that if it makes sense to have a higher density, you don't need to try to kill yourself to get to net zero.
There's another advantage that I never hear in conversations like this, but I hear in other conversations, which has to do with the quality of power that you can deliver with renewables. So if you have a microgrid, so you are safe from power outages, we live at a time where if the power goes out, it's a disaster for businesses, and with people working from home, it's a double disaster. So being able to say through a microgrid, we have high quality power, we have what Google has, and being able, that is a value add of significance that I never see sort of pulled out in these discussions of, we're better than conventional. We don't, you know, we're not just saving money, but we actually are delivering a better product.
You know, and that's the kind of systems thinking that like Rocky Mountain Institute does with, when they wrote the book Reinventing Fire. I mean, I think that those kind of interactions like you're talking about is like, it's not just I have more power because of solar. It's like, how does that interact? How does that change the nature of the grid? So yeah, I think you're right on. I mean, I you know, you start doing.
If you need help, if you ever need help sort of massaging that message, call me. I will help you.
All right.
Well, Janet, for example, on this project, there's no area for battery storage to be placed. And I think that there's some limitations still on storage of energy to be used during outages. and maybe more information than I do, but I know that that's one of the functioning limitations to the microgrid conversation now. And, the amount of energy that this building uses to be stored on site for, extreme weather events would be substantial. Like Tony said, though, the great thing about Passive House in a really tight and efficient enclosure is that you don't need to spend a lot of energy heating or cooling in extreme weather events. You just need to make sure that people are getting fresh air and maybe the refrigerator running. So really,
yeah.
About that. So,
well, I just want to, while Scott attends his meter, I just want to say that this brings up another topic, which is building integrated vehicles and different ways we can integrate batteries into buildings. And electric cars are one of those ways that, typically you're going to be using the building to charge the car, but then in a power outage, the car can be charged in the building. I mean, the size of a battery in a Tesla car is way bigger than a Tesla Powerwall. So if you can get that building integration with your PV and, submeter, bring it back in, that's, I think, part of the future of a more resilient power system and grid. But I just wanted to bring up another topic here, which is that we do not have EV charging in this building. And I just wanted to bring up, if people are thinking about doing multifamily, that Phius does require that you are ready for EV charging. But we did some calculations and we approached ICCF, who's ready to give us this grant money, to say, hey, we'd like to provide EV charging, but we can't get to zero with it and everything else. They're like, well, can't do it then. Or if you're going to do it, you have to offset it with solar on site. And we're like, well, we don't have any room for solar on site. So we're going to wire for it, run some conduits, but it's going to have to go in later, which is really a shame because, I mean, what we need to be doing with all appliances and vehicles is ending gas. We don't want to be buying a gas vehicle now that will last past 2050 because we need to be off of fossil fuels really by like 2035, 2040. And so, I mean, like, it'd be good to have all those parking spaces with an EV charging, but it changes the energy picture. All of a sudden, where you used to get energy at a gas station, now you're getting it at your house at night. So it brings the energy demand home in a different way for transportation.
I think it's an interesting conversation too, because with vehicles, that load was never on a building before, but now with EV vehicles, it is potentially on, who's responsible for that load, because it does add a substantial amount of energy use that if you're needing to hit net zero is hard to accommodate. And I think Tom, I think you mentioned batteries, bidirectional charging, all that stuff is really awesome. And hopefully we see that in the near future. My understanding is that Tesla car batteries are not bidirectional because they want you to buy the Powerwall product. So why do they have a Powerwall product if their car batteries do the same thing? So we're in a bit of a, catalyst.
Maybe it's not there. Hey, Scott, Tony has a question that I wanted to ask you about also. He says, curious how the tenant or house meters are going to work with the net zero aim. How are you allocating the PV? And that was something that we had to really go around with ICCF. Do you want to describe how that interconnect is working?
Yeah, I'll do my best. So what ICCF is looking for at the end of the day is the house meter, the meter on the main panel will be net zero across the year. So the building needs to produce as much energy as it's using across the entire year. If we go back a couple slides to that Sankey diagram, Tom, where we show the split between the house and, so about 50-60% of the total energy use is going to be on the house, which will be covered by the net zero energy agreement. So heating, cooling, ventilation, all the common areas will be covered within the free energy from the solar. There's still going to be individual ComEd meters per each dwelling unit, and those tenants are ultimately responsible for paying the energy they use. And then the energy produced on site actually ends up crediting OPRC's ComEd account so that they can use that energy across their portfolio of projects. And then the 20% affordable housing units are going to have access to that on the back end. So it's like a common accounting exercise where they'll be able to offset their individual meters, because that was part of the ICCF agreement, that affordable housing units get priority and access to the renewable energy. There was talks, and Janet, I don't know how you feel about this, but talks that this building essentially operates as community solar so that the individual market rate apartments could buy into that arrangement.
My background is just weird, and right now I find myself deeply involved with two enormous, one's a REIT, one is known for its work in private equity, buying lots of property and talking about building for rent at scale. And some of the builders that they're working with are very interested in this, not necessarily experienced. One of them that's building some high-end homes is building in to their garages, where you can put the batteries, where you'll be able to plug in. So they're already looking at this. So when I say scale, I really mean not just how big a building could be. I'm talking about how many buildings. How does this, to have sort of a Saul Griffith grand idea, how do we get this to grow really fast?
God, that's the $1 million question. It's the
well, actually billions and possibly $1 trillion question.
Yeah, right, exactly. Yeah. I mean, that's where we need the thinking to accelerate our push for clean energy. I mean, a lot of it's got to be decarbonizing existing buildings. It's not tearing them down and building new buildings. So, yeah, I don't know. I think we should maybe have that be a topic for a future presentation. I actually have to go to hear some jazz right now, so I'm going to leave this behind and go down to the CSO. But yeah, no, not an easy answer there.
Yeah, Janet, I wish I knew too. We're looking. This is unfortunate, but it's easier to plan for that.
It is.
I'm sorry. I just super quickly. So we're working on a master planning development outside of Chicago, where they're redeveloping a large area, and they're not necessarily starting from scratch. They're reusing any buildings that they can, but they're going to be building much more. And in that scenario, we do have the opportunity to look at more district level systems. We have the opportunity to look at microgrids. We're going to be able to do electrification. I hate that I have to say this, but it's easier to do if you're starting from kind of zero. In order to switch over a community like Oak Park, you need to electrify everything, interconnect everything, make sure that energy is being produced where it can, and then there's enough energy storage to offset things if the grid goes down. I don't know.
I'm in the midst of writing something that, one of the big trends in real estate. So I've gotten really interested from that angle, not just architecture and engineering, but from the real estate angle, in wellness housing, which has a buzz to it and could even lead to well washing. So it's a little, it's a little whatever. And I'm in the midst of writing something that connects all of the sort of loose definitions of wellness all the way around to lead well, passive house, and then taking it a step beyond, looking at what MIT Real Estate Innovation Lab is up to, and then taking it all the way to Amory Lovins and aggressive integrative design approaches. So keep me posted in what you're doing. I'm really, really interested in this.
I think that the wellness component of passive house maybe takes the back seat sometimes, because it's usually energy, reducing demand as much as possible. But at least market rate stuff, the non-passive housework I'm doing, there's still a big push for gas cooking. A lot of people don't want to do the proper ventilation design. there's a really, from what I'm seeing, a really big discrepancy from a wellness perspective about what's being built today versus how it could be built to promote occupant health and wellness.
Well, that's basically what I'm right in the middle of, and trying to get the Deepak Chopra contingent over to the Amory Lovins contingent and seeing if I can get them together.
Yeah.
Wish me well.
I do wish you the best. The sad thing is, if you've worked in the city of Chicago, at least on a multi-family level, they still allow you to ventilate from the corridor. So you dump all your fresh air into the corridor, and then it transfers into your units through air transfer. And a lot of market rate developers want to do that because it's cheaper. You don't need to duct to every unit. You're just dumping air very simply into corridor, and then it gets drawn into those units. And there's a lot of, transmission you need to account, like COVID stuff. How do you account for that? It's very scary. And at least in the city of Chicago, there's a lot of things.
What I'm looking at is national. It's all over the place, and it could be at scale with extremely deep pockets. So, but the people with the deep pockets haven't got a clue. So what I'm trying to do right now, and I'm weirdly enough in a position to do it, is give them a clue. So I'm really interested in what you're working on, really interested in Passive House. So this has been a treat. Thank you so much.
Yeah, my pleasure. I wish we could have provided more information about the microgrids. I think if you're not familiar with what Bronzeville, I mean, you talked about IIT.
Yeah, actually, I am. I'm familiar with the whole, with all of it. And PG&E in California has gotten into them because they keep getting sued for starting fires because of the big grid. But it's also that the big grid is falling apart. How are you going to spend your money to get to the 21st century? And I was writing something that was looking at economies and looking at what China is doing in terms of its grid. And they're doing to super grids altogether, as well as microgrids. They're creating a grid for the 21st century. We've got a grid for the 19th. So anyway, but I've got to run too. So, but thank you so much. That was so interesting, and keep me posted.
Yeah. Thank you for the great questions.
It's kind of what I do. Thank you so much.
Come back and visit us every month, all of you. Thank you all. And thanks again, Scott and Tom. And we do hope to see you next month. It's going to be another awesome presentation. A lot of forward thinking on embodied carbon. So join us then. Thanks, everybody. Have a good night.
Bye.
Scott, can I ask you a question quick?
Oh, yeah, sorry.
Yeah.
How did you handle with her question about indoor air quality brought up question about the range hood issue? What did you do in this case? Did you do range hoods? And were they direct exhausted?
Yeah, good question. This approach on this building is a general exhaust that runs at the continuous rate that Phius is looking for, 25 CFM. And then there's a recirculating
hood okay.
over the, yeah. But this is, I mean, this is something that I've asked at other Passive House gatherings and conferences. I'm not convinced that this is the best approach from an air quality perspective.
Yeah, probably not.
There's a lot of research and data that suggests direct vent at the source is really what you need to do if your priority is indoor air quality. And everyone in the Passive House world groans at that because you have a lot of heat loss, and then you have makeup air you need to provide, which is a big energy penalty. So
it can't be run through the ERV, right?
No,
not to mention the cost on a multifamily market rate thing too.
Yeah,
right?
Yeah, big cost.
And is there a dryer in every unit too?
There is a dryer, and it's a heat pump dryer.
Oh, it is.
I don't remember what manufacturer, but that's the plan. Yep.
Okay, so those aren't direct exhausted. So okay.
Nope, and that's something, that's another thing that we've been studying. Well, not so much on the heat pump dryer, but on the hot water heater, is what sort of penalty do you get if it's located in your unit? So the heat loss in the winter that you need to make up for. What's a good approach there? We toyed with the idea of having them on the corridor perimeter, so kind of like cutting them out of the dwelling unit boundary, so to say. And then that those heat pumps exhaust the corridor, and the corridor becomes this like semi-conditioned weird space.
Cold corridor.
Yeah, cold corridor. And then there's, I think I mentioned it in the early minutes of the presentation, there's these plumbing engineers out of the Northeast that are doing these really cool centralized heat pump water heater designs that string together a bunch of individual units, and they're split systems. So they have outdoor units, so you're not taking that heat loss in your building in the winter. And they run off CO2 refrigerant, which is more efficient and better in colder weather.
Yeah,
like kitchen exhaust and hot water heating is the two next big things to kind of revolutionize.
Weak links. One last question. This is probably more a question for Tom, but since he's not here, I'll ask you.
I'll try.
The decision to put the photovoltaics on a kind of overhead screen, was that kind of just to optimize how much photovoltaics you could have? I mean, would you have lost some if you put them right on the roof, or just to eliminate shading, or to provide for more accessible roof area, or how did that decision-making process go?
It ultimately was a owner project requirement that there was an occupiable roof terrace. That was a really critical piece of what they wanted to deliver. So from the get-go, solar on the roof had to be raised off the surface
just to get enough solar to get that roof. Okay.
Yeah. And by virtue of doing that, do you alleviate the 3-foot fireman rule as well then?
That's a good question. To be honest, I don't know where we land, but if you remember back to the diagrams Tom was showing, I think there's instances in which we're slightly over the vertical profile. And I think that there weren't concerns about that. At least we were told.
Is that 3 feet around the perimeter, Tony, or is that all that is?
Yeah, 3 feet around the perimeter for firefighting.
So they can get up there and put a fire out if they need to.
So I think the argument is that they can do that from the roof deck then if it's elevated.
I'll say it's caused all sorts of other coordination issues.
Well, it adds a lot of expense to your photovoltaic because you actually have to purchase a whole, instead of just setting them on the roof with a little ballasting, you have to build a whole steel infrastructure for it.
Yeah, but all that said, it's about 30% of the grant goes to producing energy, and the other 70% goes to offsetting, increased efficiency costs, extra insulation. It's not as much as you would imagine to be a net zero building. That grant isn't all going to solar panels, which
right. No, I understand. Yeah, I know the grant. Okay.
Yeah. Roof penetrations, all the structure. There's a lot of point load there that needs to be taken care of. Tom didn't touch on the balconies, but there's a lot of wrapping balconies that need to have thermal breaks too. A lot of interesting considerations to be made.
A lot of details to look at. Yeah.
I'm glad. Yeah.
Otherwise, you got to do a lot of therm calculations, and those aren't fun. So.
Don't tell Tom, but I'm glad I'm not the CPHC on this one. The amount of therm modeling that's going to be required.
Well, I didn't mean to cut anybody off, but I'm glad we got a few more questions in. Any last call for questions? Or any last questions? Call for last questions?
I'm glad you touched on that VRF system and why not to use the energy recover on that, because the first project I was a passive house consultant, they did use the energy recovery, but in looking at what they did, they gave really no consideration as to why you might have a heating demand and cooling on the other side. And so they didn't branch it correctly. Like you described, if you would have had to go on horizontally, just to move it from north to south, because there might be a situation where you might need heating and cooling. But in this school, I couldn't figure out, well, the only possibility they would have is in the morning, it might be hot on one side and cooler on the west side, because it was an east-west kind of subdivision, but they didn't zone it that way. So even if, I can't imagine it's going to be worth the money they paid for it.
We did. I should have noted, and I forgot until you just mentioned it, but there's one outdoor unit that is designed to be heat recovery, and it's the unit that serves the common areas and the lobbies. And there's a vestibule on the top of the roof deck. We found that it paid off to have that on that outdoor unit. From a conceptual level, on a passive house where your loads are pretty balanced, right? I just conceptually don't see the heat recovery being worth the extra cost and extra, coordination and everything. Yeah. So, yeah.
Especially when you can get your glazing ratio down below 30 too. So that helps.
Yep, definitely. Yeah. On a school, maybe it's different though, because you have a lot of different loads in the building. And
yeah, I mean, I guess one classroom could be, I mean, it's still a big spread. I mean, because the cooling doesn't come until 77 and your heating comes, it's just like, well, it's a 10-degree spread if to require heating and cooling in different spaces. And your ERV was a strict ERV. It wasn't a DOAS unit or something. So it did no preconditioning of the air.
It is a DOAS. It's the Swagon unit, but it's raw air. So there's no coil.
There's no coil in there. Okay.
We needed to go that route to get the highest recovery efficiency. The one that does dehumidification and some of the other preconditioning had I think it was less than 80% recovery rate. And we found that would be a deal breaker on the heat load.
Okay.
All right, I'm signing off. You guys can stay, but I'm leaving.
Likewise. Thanks, everyone.
Yep.
Right.
And now.
Cheers.
Thanks, guys.
Take care.